to present this talk. Simon Hausman actually did this talk last year. My hope is to reiterate his points and provide some updates. Today's topic is microcontroller. Actually, let me stop my video. All right. There we go. All right, so let's get started with a little bit of background. Microcontrollers with displays are becoming more commonplace nowadays. Appliances at home, like thermostats, refrigerators, coffee machines, toothbrushes even have displays, some of these being touch displays. Of course, customers want these displays to work smoothly, seamlessly, just like their smartphones or their smartwatches, and devices perhaps with a bit more expensive embedded processors like the IMX6. So one reason to use microcontrollers is that they're generally much cheaper than, say, an embedded IMX6, but they're hard to program, and it's difficult to get that smooth kind of experience. So you need to know a lot about low-level APIs, about how hardware works, and how displays work. And you need to really squeeze performance out of those inexpensive devices to get a good user interface. That's where Qt comes in. We'd like to simplify the programming for you and make the process a little bit more fun, a little bit less daunting if it feels that way now. And for microcontrollers, the folks at R&D have gone back to the drawing board with Qt for MCUs to really address the memory and performance requirements. So to get you something, excuse me, I have a bit of a cough, sorry about that. To get you something really good, something really small. They built a new graphics engine specifically for microcontrollers. It's called Qt Quick Ultralight. It's the combination of several new techniques and things that weren't part of upstream Qt. So there's a lot of pieces of the project. The idea is to show you some of these building blocks of Qt Ultralight and to show you how it works. The thought is that if you roughly understand how technology works, you have a much easier time diagnosing issues, performance, to get the most out of your device. We'll start with a quick outline. These are the building blocks we'll be touching upon. We'll go over the general workflow and what to expect, what the environment's like, and we'll dive right into the event loop, which is not quite the same as when you run Qt on embedded Linux. We've added RTOS support for some devices. We'll talk a little bit about that. We'll talk a little bit about rendering, which is also a bit different than Qt on embedded. Then we'll talk about how we pack resources into Qt for MCUs, how we produce graphics, how images and translations are handled. And you may have heard in other talks about how we're redesigning the way properties and property bindings work, how they work in Qt, and that work actually originated in Qt for MCU project, and we'll go over a quick preview of that. Finally, we'll show this compiler that compiles QML code ahead of time. It's for us a whole new way of generating C++, and we'll cover that. So let's get started with application building blocks. We assume your application has at least some C++ code. We'll give you the ability to use QML in a way that you might already be using, or you might already be used to. You likely need images in your graphical application, so there'll be those. If you intend to show some sort of text in your application, text is rendered using glyphs, and glyphs are in fonts. And we assume your app will have true type fonts. So fonts are considered an essential resource to your application. If you'd like to target more than one language, we allow for translations, and we consider them really important to have, especially when shipping to international markets. You can still use the same tools like Qt Linguist and LUpdate to extract translations. It's not so much of a change for the developer perspective, but we have changed the way that translations work on the inside, and we'll show a little bit of that. The application building blocks need to be pushed into the build system. So we've chosen CMake as the build tool for Qt Quick Ultralight, mostly because the majority of C++ developers know it and they're familiar with it, and it does the job really well. In fact, Q6 upstream as well, we're moving in that direction. So we provide you with the integrations in CMake to allow you to do things like inject files, set properties, all of that. Eventually, CMake calls the C++ compiler. We'll take care of picking it up from the SDKs the board vendors typically provide. So we provide CMake toolchain files to pick up the correct compiler, etc. And we have a bunch of other tools that take care of images, fonts, and QML files. We're labeling this as a compiler, but it's actually a collection of programs that build tool will call to process and compile the QML side of your application. So we also assume that everything will finally be all linked together in a static binary. We also link in support libs from Qt Quick Ultralight, but eventually everything comes together as a static binary. Generally, there's one final image that's created, and after that, there's no extra dependencies or libraries. Even the bits of C runtime that are used is all linked into the static binary. So all of that comes together as an executable, sometimes a hex file, and that describes where everything goes. Then you have to flash it onto the device. You can do this with Qt Creator. We provide you with a makefile targets to do this conveniently. Certainly, certain segments of your binary will end up in different areas. Code ends up in some areas, data segments in others. Images may end up somewhere else because the microcontrollers, with microcontrollers, certain areas might be different, might have different performance characteristics when it comes to accessing it. There are areas, there can be areas in the RAM that are very fast to access from the processor because the processor caches them, but they might be slower to transfer to the frame buffer, to the area that's going to show up on the screen. On the other hand, there's memory areas that are slow to access from the processor, but they're very fast and efficient to access those graphics accelerators. We give you a bit of control, especially as the versions move along. We make use of the ability of these device characteristics to get the best performance. Images end up in different sections than, say, your data structures or your code, and you can even now control this to an extent. This is sort of the rough idea. When all of this is flashed onto the device, you're going to power it on and hopefully everything will work. The processor will start running at a specific memory address, which is where we place some initial board initialization code, or that comes from the board SDK, and then that takes like really basic things like setting up the clock, initializing the RAM controllers, the memory mappings, all of that. We take care of all of that, so it just works. Unless you'd like to really deal with the low-level programming, you don't have to. So once we're at that point in a normal Qt application, when you're in main, you run Qt application exec to enter the event loop. And let's talk about how that happens with Qt for MCU. In the case of MCUs, we don't by default have an operating system. Things run on bare metal. The event loop starts with an instruction which is called wait for interrupt. And all it does is puts the processor to sleep. When it's sleeping, it's waiting for an interrupt. Interrupts are external triggers that have the ability to then interrupt, or in this case, wake up the processor. There are different ways to trigger an interrupt. One scenario might say, one scenario might be you tap on the touchscreen, and it's an external event that's a wake-up call for the processor. If I'm tapping a button or something, something needs to happen in response. So the processor wakes up, for example, we provide a handler for touch events, and we receive data. There's no dedicated touch interrupt on these controllers. Usually that goes through a different serial bus. But for the sake of simplicity, I'm saying there's a touch interrupt. So that's where we read the data from a touchscreen. And where did you touch? How many fingers? We collect that data, and now we quickly post it onto the event loop, and then we return. There's another type of interrupt that we care about setting up, which is the timer interrupt. We typically set it up to fire every millisecond. So every millisecond, the processor might wake up. We typically just increase a global variable that counts how many milliseconds have passed. This allows us to know where we are in animations, etc. So in Qt Quick Ultralight, you'll be able to define your own interrupt handlers and to integrate them into this event loop. So you can post your own events, react to them. The two we're discussing right now, we provide defaults for. So after the interrupt's woken up, the processor is going to come back from this instruction that we originally ran, and it's going to resume running code there. We call this wake up. So when I touch something, I post the touch data into the touch event, into this event loop. We're going to take that out, and we're going to process it. For a touch event, that might mean finding the item that you did touch at those coordinates and that finger, notifying the item, and maybe running some code you specified that on button press, some business logic happens. Another thing that we automatically do after we processed any pending events is we look at animations. So animations that might be defined as in 3 seconds, this element should move from, say, point A on the screen to another. Given the timer we've counted earlier, we can see where we are in the animation right now and how our item needs to move together or change coordinates or scale or whatever it is. This is where we process the declaratively specified animations in QML. So finally, we have to produce pixels onto the screen. And we're going to start with, I'm going to start painting stuff. Excuse me. Here's the last step. Since we've woken up at least once every millisecond, we don't always need to paint something, but maybe every 16 milliseconds to maintain that high 60 FPS. Painting's quite interesting on these things. You have, say, a memory area that you say is my frame buffer. You typically allocate 2 of these, and then you tell the display controller, hey, what's on the screen, show it on my first address. And then you prepare the next one, and you just tell the display controller, hey, now show the address, show this from the second address. And it's kind of like a pointer that you direct, and it's an interesting low-level way of rendering. You can reuse what's in between those two, so you don't really have to start from scratch. We can talk a little bit about that soon as well, but this is roughly how the event loop looks like. So we put everybody to sleep, consume little to no batteries, use their hacks on the device. Typically, the steps of the event loop, similar to how Qt works on embedded, those kick in. Okay, so in version 1.0, there was only one option, which was to run on bare metal. Version 1.1 just released, and now we have support for freeRTOs on some devices. I'm not going to get into the details, but I thought it was worth a mention because now the event loop's a bit different. Long-running tasks in the background are important use case for real-time operating systems. An example might be streaming music from like the internet while you're maintaining a responsive GUI. And basically, you need in real time this data to be streamed. While that's happening, you need to show the GUI which should update the progress, maybe stay responsive and be usable. The way to do this is via multitasking, and RTOSs allow for that. So what does this mean to run Ultralight and freeRTOS? Essentially, we create a task in freeRTOS that calls app-exec and then runs forever. We can create another task as well where we might say do a constant LED light trigger or your music is streaming in, and that's all that needs to be done for now. Excuse me, sorry. Right now, there's a limitation that tasks are all the same priority. We still need to enable time slashing and preemptive schedule for those users that might want to assign priority to tasks. So if you want to assign priority to rendering or some other task, we should be able to do that down the line. So let's take a look at the last step of the event loop, that is the painting. Let's briefly go over how we render things onto the screen. Imagine a scene of QML items. Let's assume there's a root item. Let's assume that the root item has a rectangle, and inside the rectangle there's some text. Maybe there's an image somewhere. Maybe the rectangle looks like a button or something. So as you might know from QML, you construct the scene and it creates this hierarchy. This creates a tree of items, as we call them. And so we have this objective to represent them on the screen, to visualize them correctly. There might be some items obscuring other items not visible at all. So there's a certain amount of work to be done. This diagram is a simplified diagram of the rendering algorithm. It does a lot of things that we don't do when we render OpenGL typically. One of the things we do is we compute which areas on the screen actually have changed. We only change, say, the pixels in the bottom area if the thing that's happened is like a button's color is changing. And like the buttons area, if like, say a button's changing color, that's the only pixels that you want to change. The other stuff we don't really need to touch. The button triggers, say, spinning animation on another part of the screen, then now you have two areas that you need to do. And all of these are typically represented as a series of rectangles. So there's a series of rectangle areas. When we compute the change list of rectangles, we call them dirty, and they need to be redone. Usually, the affected area is a little bit less than the entire screen's area. So ultimately, we end up producing less pixels than the entire screen area, and that saves us time, gives us performance. Another thing that we do in an early step is we compute which items are obscured by others. An opaque rectangle on a green background will hide anything that's underneath it. So if there's text underneath, that text won't be visible. We spend a little bit of time to compute which areas are obscured by opaque items in your scene. This allows us to skip rendering for the entire items altogether. After the two prep steps, we can enter the recursion into this tree. So we start looking at each individual item. Items have children, so we look at the item itself, then we look at its children, and then we determine based on the data structures that we built up. If we determine the thing that is underneath the item, it won't be visible, but then and we don't have to do anything. We can skip it, we can save some work. And then that's the common pattern anyway. You have items hidden, then they only show up when you start an animation or something, and this can help a little bit. Also, if something is not changed, like we know it's not touching or intersecting an area that should be changed, then we can avoid a whole bunch of work there too. So those are two primary kind of like escape conditions that allow us to avoid further work, but eventually something will be visible on the screen. And so then we have to look at what it is that we should render. And there's different primitives. We call them render image, render rectangle, and let me explain those a little bit. So it turns out that all of those 2D interfaces, they can really be defined in terms of primitive rendering. They can be simplified very much. So we'll say that there's two types of operations or primitives, and you can draw rectangles or you can draw textures. A rectangle is just a shape. So what we really mean is that the rectangular area that is where the color of each pixel is all the same color. This can either be fill color or say a green or red rectangle, or that everything in the rect shall be green, or if it's a blend operation, so we might say I have a green color of every pixel, but I want that green to be blended in with what's underneath. And that can be different. So in both cases, we're basically just filling a rectangle. The other primitive on the right side is drawing a texture. So color texture is really just another name for an ordinary image when every pixel can be a different color. And if you show text, that's a special type of image. We treat this differently. It's called an alpha map. So that's a texture that only has transparency values. It's a very efficient representation of glyphs, which are used to compose text. Otherwise, when we say color here, we really mean RGB usually and an alpha value. For alpha maps, that is glyphs, we say we only have one value, which is the transparency value. So we combine that with the color of text, and then that whatever color your text you'd like to use, and then we blend those two together with a background to produce the color text. So there's a special case, which is transformations. They're special because in our code base, these typically require quite a bit more work because it makes things more complicated. If you have just a plain rectangle, it's pretty simple to get that onto the screen, but once you start applying transformations, it gets complicated. Let's say you start rotating things and your geometries get a bit more complex. You suddenly have to start rendering lines, and then you have to find intersections. And this is special, slightly slower code path. And we don't do all the transformations because it would be really slow, but we support some of the more common ones. So really everything that you might have seen so far, like the demos and all the beautiful round watch faces on the L4R9s, if you've seen those, it's basically filling rectangular areas with colors or images. And it's really primitive. The magic is composing all of that in the right order, at the right dimensions. And that's what makes the user interface like the beautiful thing that it is. So running smoothly, of course, is important. It's important that things run fast. And on microcontrollers, that requires a little bit of help. We do everything in software. So we have everything implemented in a way that is a reference implementation and produces the correct result. It runs on the microcontroller itself. But while the main processor is busy producing those pixels, blending those rectangles, etc., it can't do anything else. That's kind of a shame, and especially if your scene is complex, that can really bring you down to like very few frames per second. Fortunately, people who make MCUs have been in the business long enough to understand that they need help over here, and so they typically provide extra dedicated chips that provide you with functionality to do graphics in a fast way. So early operations we showed with rendering primitives, they have help for that. So what those chips allow you to do is kind of copying memory. All they do is copy memory from one area to another. Typically that means copying images. They're not just another memory controller or a DMA controller that copies memory. These chips are also aware of graphics a little bit. They're aware of blending modes. So you could copy memory from one area to another while also applying transformation and at the same time a blending mode. They can do solid fills of rectangles typically. Some of them can also do transformations. Scaling sometimes they can do, 90-degree rotations. The really nice thing is this can happen asynchronously. So you can batch up these operations and say, by the way, I want to copy this, this, and this, and you send that off to the graphics chip, and then the processor can do further work. It can continue recursing through these items. The item tree, for example, that we talked about in the last couple of slides, or it can find other items that are not obscured. And this really makes a difference between crawling to like 15 to 20 frames per second and hitting that 60 frames per second. So Qt for MCUs supports these hardware accelerators. As more boards are supported, the list should expand, but there is at the moment support for EXP or an XP family of devices, ChromeArt on the STM devices, and the RGL on the RH850. So we can get stuff onto our device. We can react to the touch and event timers. We can hopefully produce a picture on the screen, but your interface is not just going to consist of solid color rectangles. There'll be other stuff. There'll be images. There'll be text, and you'll want to have translations with different text depending on what translations, etc. Let's look at how we handle all of that in Qt Quick Ultralight. And to do that, actually, let me do a little bit of live coding. Let's see. Let's not show you my chat. Let's get in here. All right. So this is sort of a minimal sort of an application in hello world type of application in Qt Quick Ultralight. Up top, we've added support for a keyword, pragma main. This allows us to skip a lot of the work of writing the main function. We can actually start Qt Quick Ultralight application with just the QML files. It's also possible starting 1.1 to add your own main function if you need to do something special like initialization. This is one way to do it. So it's a rectangle, and it's like the one you know in QML. We have a backend that uses Qt itself to show Qt Quick Ultralight application on the screen. which is a convenient way to like run debugging. So what I can do is something like this, even without a device. So that's nice. We know that our application works. First thing to do, I guess, let me split the screen. And here, show the CMake file. We have the Qt Quick Ultralight package. We have the executable. We have a function in our CMake API that's like target sources, but we call it target QML sources. It allows us to associate QML files with an executable. So there's plenty of other of these CMake functions and keywords that allow you to do things like add translations, pull images into resources, or tweak how images are handled. So there's, that's exactly what this is and this is. And then eventually we have to link things together. So this little line over here, this actually sets the QUL OS target property to contents of whatever the OS variable is, and performance additional setup based on it. So in our case, we're on bare metal, we're fine. You can do something like the OS is freeRTOs, and you can sort of set that value in CMake. So we compile this and we instruct CMake to do its job. The demo.qml file gets compiled into a header and a CPP. You can actually find these files in your build folder. The header file actually looks like this. So this is my build folder. This is what comes out of the demo.html.cpp. So note that our QML item, it's translated into a struct. There's struct subclass is a rectangle, and it's got a constructor. Now, if I add rect and items inside my QML file rect, let's say rectangle, let's give this an ID of friend, let's say another item. And if I do this, if I hit save and if I build, and then look back at my .h file, we can see now that I have two new members inside that top level structs, which are also trucks. So when we instantiate the top level demo struct, we also at the same time instantiate the rectangles and the atom inside. There is no extra memory allocation involved. It's all done in one go. If I allocate the top level demo, I'm done with everything else. This is a pretty efficient thing to do, and this goes down into the nesting, and this changes semantics a little bit. You can't just, for example, take an item out and move it somewhere else, but in practice, that's not an issue. Doing things this way allows us to very efficiently avoid memory allocations when instantiating items in QML. So let's remove those two items that I just added. Let's save. Let's actually remove them. Let's save. Let's rebuild. And now that this is a little bit cleaner, I actually want to show you that CPP file. Yep, see how all that's gone. Okay, so the CPP file, let's look at the main function at the bottom here. This is where we create a root item in QML, this guy right here, right? This is allocated in read-write data. We have an application object. We notify that we set a root item. And then when you see app exec, this is all generated code. So it should look somewhat familiar to the Qt code you might typically be used to. And if you write your own main, you do something like this for setup on the Qt side. There's this concept of language property, but we'll discuss that in a little while. So right above, you can see color, this color value. This is a property in our demo implementation. The color above is a property for the rectangle type. So yeah, so the color is a property for the rectangle type under the hood, and it's just another C++ member. Our constructor for demo, it just takes the color property that we have and it assigns it this value, this hex value. And you can really kind of read this alpha RGB, the R being the only value for the green. So the G being the only value for the green. So that's fine. So okay, we know about rectangles. Let's talk about images. How does an image work? Before I actually do all of this, let's make sure that we have an image file. Whoa, another meeting, guys, I'm sorry. I gotta go. No, I'm kidding. So let's start by changing through, okay. We have this added resource that is our image file. We're set here. And in the code, what we're gonna do is we're gonna set this source to correspond to that. The Qt image is just a file that I've already set in the same folder. And let's make sure this runs. Okay, good. So this is my queued image in the same main folder. Okay, let's look back at our demo.h. Note that the root item is derived from image now. And let's look at the constructor for the demo real quick. Okay, note that there's this value set in source. This is a handle, a type for raster buffer, and let's see what it's pointing to this cute image handle. If you kind of scroll up, you see that there's this pointer. And really, if you look in your folder, the same build folder, and kind of look for your image. Where'd you go, image? There we go. Right? Let me make sure I build this right. There we go. Okay, good. Whew. Got nervous for a second. When I look inside of it, sure enough, there's this handle, right? And it's assigned to the address of this raster buffer. The raster buffer in it has this array, and that's basically all of your image data. This is your image. It's not the original image. The raster buffer is a struct. It's static. It's read-only. It contains only the predetermined, pre-processed image data. Sorry about the helicopter noise. That's just the world, I guess. So we take the image data that you specify. We look at it and it might say, okay, this is a 32-bit image, but the target device is only 8-bit per pixel. So we might as well decide that at compile time. And we can say that if it's a large image that you have and it turns out really there's only pixels at the center and the rest is transparent, we can process that down to a lot less. We'll only embed the real data that has pixels. We can do this on multiple regions. So if there's a large image that has real data in 2 different areas, but the rest is transparent, we'll basically embed the 2 sub-images. And when you use images, we don't load them dynamically. We look at the file name at compile time, and we look at the image that you're pointing at, and we're going to go ahead and embed the image right away. So we process the images at compile time, and we also, by default, decode the image. And with 1.1, you can actually embed the image as a raw or PNG, but by default, I believe the image is just decoded. So the result is when you render UI, you have all those images right there in memory. All you really need to do is copy them. A lot of UI work is copying images from the same area into the screen, onto the frame buffer. By not having to do this any other extra processing, this can be done very quickly. And in fact, there are customization options in 1.1 for all of this as well. So we talked about images. Let's talk text. So I'm going to create a text. I'm going to set the text value. And I'm going to set it to something actually I already wrote a translation for. Just cheating a little bit here. And let's give it a size. Let's say 25. And let's give it a color. And let's call it salmon, because that's what our default will be today. Let's build this. Let's run it. Okay, good. We have text. Same as before, let's go look at the generated CPP file. Demo.cpp, where did you go? Okay, good. Let's start with the demo constructor. We can see how the appropriate properties are represented: the color, the size, and the actual string. Here's the actual string. So let's look at the folder again, and you'll see that we have this QL font CPP. Okay, and again, we've generated a lot of stuff, and this is basically the font that you're using. Rather than using alpha maps, these are the alpha maps that you're using, the glyphs that you're using. So we also embed kerning tables, etc. We have character maps that allow from characters to glyphs. Ultimately, we can only embed those glyphs from the font that you're actually using. We ignore everything else. And then you can use something like in QML, I think it's font.unicode coverage in QML to add to a list of Unicode glyphs that are compiled into the binary for this font configuration. So that gives you kind of a static text range. It's also very efficient. So there's another QML element called static text where we just embed the glyphs directly, and you don't even have to go by strings anymore and map it. And the pipeline of fonts, I believe, is improved text rendering with monotype Spark, which enables support for any language, includes complex scripts like Arabic, and Spark is also a bit more memory efficient in general. Finally, I want to talk about translations. So the way we're going to do that is I'm actually just going to make sure, first of all, in my CMake text file that I have this little entry right here that points to my translation file. And then we're going to use QSTR around my text. Let's build this. And then let's look back at our demo.cpp if I did things right. And this is where we have the translations embedded, and you can see it right here as a string. So when we use that string, we'll end up pointing straight into this array with only the translation that we use. You can specify at build time what translations you want and what we'll embed, and we can embed them right away for you. So in this way, you can create an image for different languages if you want, or if you'd like to, you could create an image for multiple languages as well. In either case, it'll be embedded as UTF encoded strings into the code. Okay, that brings me back to my slides. Let me try to load them up. So to summarize, we treat images, fonts, and translations very differently than we typically do in Qt. In Qt, images, fonts, and translations are all loaded at runtime on demand. Here with MCUs, we embed for images only the bits that are necessary. The same goes for text. We embed only the glyphs that we need. And for translations, you get to choose, and we embed the strings of the translations right away. So, all right, we can do graphics. We can embed all these images, text, and translations. But the beauty of QML is that you can expect relationships between objects in bindings. We've done a completely new build system. Let's quickly go over that. Oh, sorry. We've done a completely new binding system. I'm going nervous a little bit. Completely new binding system, and let's go over that quickly. Okay, so hopefully you've seen something like this before. A rectangle with a padding property, and then the height's calculated as width times 2 plus padding. We know that when the width of padding changes, we recompute the height by recomputing this expression. So traditionally in QML, this is built on the idea that objects have properties. Classes that are used to instantiate these objects have functions. So you have to declare setters, getters, and signals, and you have to emit, or it's generally being emitted. The signal has to be emitted when the property changes, and all of this belongs to the class. So at runtime, then this belongs to the object. So the object is responsible at runtime for emitting the signal, and this can be tricky at times because it's not always emitted right away when you set the value, but sometimes due to implementations, it's implemented later. Everything is traditionally tied to the concept of those classes, and while that works well, it can be a bit heavy. It requires your full object model, and in the current implementation of QML, when a property changes and that signal is emitted, any bindings that depend on it, they're all evaluated immediately. And we're doing this a bit differently in Qt Ultralight. So we've made it object-centric. Instead of being all centered around classes and objects, the property itself now has everything that it needs to be sort of a full citizen in this world of properties and relationships and bindings. So a property is a template type in C++ for us, and the type is the data it encapsulates, and the property encapsulates the data. So the property has the data itself. It knows when somebody wants it, and also when somebody gets it and changes it. So properties also keep track of any bindings that query them. So while a binding like this calculation of width times 2 plus padding, while this thing runs, it queries the width, for example, the width itself is aware, oh, this thing wants to know my value. Okay, I'll give it to you, but I'll remember you. I'll keep you in mind. So next time the width changes, I'll call you back and reevaluate. This memory is one of the few things that we do dynamically in the Qt Ultralight. So this becomes an intrinsic feature of property itself, not of the object or any parallel data structures. It makes things like bookkeeping easier. It makes it lighter. So when something changes, we don't immediately reevaluate a binding. We just mark it as dirty again. We call everything dirty that we want to do later. So we call it dirty, and later it can be reevaluated. Only only when the value is actually needed. And this makes things a lot faster. The result we found is that this property system behaves in practice exactly like it did before, but it's much lighter. We can avoid many memory allocations, and the laziness of it avoids the unfortunate effect of binding storms when multiple dependencies result in multiple evaluations of the same binding, even though that's not really necessary. So we can do graphics and we can do property bindings, but we also don't have a JavaScript engine. But you want to be able to write a little bit of code in QML. You want to be able to write expressions in QML files. So this is where we've done something a bit more extreme. And we say there's no JavaScript engine, there's no garbage collector, no eval, no runtime interpretation. Instead, we want to do everything at compile time. We want to generate code that is almost as efficient or as efficient as if you wrote it by hand, except in QML files. It's a lot easier to write. So you can avoid a lot of C++ boilerplate and things like namespaces, pointers, colon, function declarations, or whatever. And the beauty of QML is that you can write all these small little expressions, these tiny little snippets of code that are really well contained. So we wanted to preserve that, and that hasn't changed. And so you can continue to write functions in QML, but what comes out of it is a bit different now, and I'll show you a bit of that. So let's go back to my code. Just give me a second. Okay, good. So I think what I'll start with is a rectangle again. I'll give it that color. Do we still want to give it a green color? No, we actually, what we want to do is we want to create an area. So mouse area. Let me just write this code up for you real quick. I'm going to fill the parent space. Fill. There we go. Area not pressed. And actually, let's have it change. So what do we have? We have a mouse area and a property called pressed. Now let's change it. Let's run the program. Let's see how that goes. So if the area is not if the area is pressed, it should be green and blue, right? Okay, good. And if it's not, it's green. Okay, so that works. Okay, what does this look like back in our demo.h? A lot more things now. So the code has changed again. This is now, there's now a struct called color binding functor. And it's a binding functor for the color. And it's all auto-generated. And it has this thing, this operator here. It returns this RGBA32. It's basically a color. So this RGBA32 is a C++ type for what the color is in QML. So this thing will contain the code. That is the binding expression. So let's look at that binding expression inside the CPP file. And this looks a bit like typical auto-generated code at a first glance. But if you look a little bit closer, you'll maybe recognize some terms that you can start to mentally reconstruct this binding expression. The R2 right here is DR is short for register because it's a register machine. These are just local variables. And if you hover over the R2, it tells us that it's a pointer to a mouse area. And there's a self parameter that gives me access to the ID names. What I want here is the self.area. And so this generated line will basically copy a pointer. And that seems pointless, but the compiler will collapse all that nicely anyway. So it's stored in R2, and from R2 it's a mouse area, and it's got this pressed property. So we get this pressed value and we put it into a different local variable, the R2 pressed. And based on really what happens to R2 pressed, whether it's pressed or not, we choose a different color and we return that color. So it might not be descriptive at first glance. Still, the code is collapsed and it's as efficient as if you were to write it by hand. And the compiler knows all about the types. It knows that we're dealing with colors. It knows that they're being assigned. It knows that there's this Boolean expression that we need to evaluate. And we can go a bit further here, actually, and write this whole thing as a function. We can make a reusable code. So what do I need? I need a function. Let's call it pick color. And we're going to say area press. We're going to give it this parameter, this argument. Let's say color. Let's type, so return area pressed equals blue or green. So depending on the value of this argument, we're going to do the same exact thing. And of course, we need to change this to pick color. And we're going to say area.pressed. Okay, so I still have the mouse area, I have the function. I think I've got everything. Let's save it. Let's run it. Let's make sure it runs. Maybe that's the test. Oh, it doesn't run. Let me make sure. What does it say here? Color, pick area, area.pressed. This should be fine. Yeah. Pressed. Of course. There we go. Whew, had me nervous there. Okay, has the same behavior. Green regularly, blue otherwise. Okay, so what's different is that we've done an annotation here with color, right? We've said now that this function shall always return a color. If you hover over this, you can even see the description. It's a property that holds the color used to fill this rectangle. This annotation is a promise that we'll always return color. So your return type should match what the color is expecting. And the same goes for parameters. So I can put in the parameters area pressed bool and put in area press as the argument and use it as a function to return area press, whatever this is. So if I try to swap the argument of like this with a string, let's try that. This shouldn't work. And let's see what the compile output says. Sure enough, it says argument contains string, but it's expecting to contain a type bool. Let's try it again. Okay, this works. So we generate a function that almost looks like it's written by hand, takes a Boolean input from QML and returns the color. The implementation is basically on the C++ side. Let's take a look at it. The .h file. So the .h file should now actually update. Let's say demo.h file. Oh, there we go. Everything goes wrong when it needs to go wrong. Oh, it's not updating for some reason. So basically what you end up in the CPP file is this pick color function usually. Why it's not updating? I might have desynced them somehow. Okay. And ultimately what you'll end up actually with is basically all of this code will end up in your function. Now that should just work out. I think it's something that's just not, it's one of those things, everything can go wrong during a presentation, will go wrong. And nothing. Oh, there we go, finally. Whew. Okay, so you had this pick color function in your .h file and all of that code that in that operator. So now your operator actually calls pick color, and the code for pick color is exactly the stuff that you were looking at before. So the implementation is basically the same that we have in the binding. Now this is a regular C++ function. You can even call this function from somewhere else, even your own C++ code if you want to, you can do that. And the function in our case, in our CPP, is not called by the, the color binding functor we called earlier, just that pick color over here. And this in our experience is very efficient, as if you wrote all of these little binding expressions by hand, but you don't have to, and you can still embed them in the QML file, and you don't have to deal with the C++ of it at all. And we generate something for you that's as efficient as that, but it looks as nice as this QML. Okay, let me stop the live coding and then switch back to slides. So to summarize again, we're quite aggressive about compiling everything ahead of time, including your code, including your binary expressions. We extended the syntax a little bit by requiring you to specify functions and what types are. Everything else we can infer. We can figure out if you have a binding expression and this is assigned to a color property or a bool property, we can figure out that the variable inside it has to be a string or you have to return one. But for functions, we can't. So we kind of changed the QML syntax slightly to add these annotations. And the really nice thing is we've also done this upstream. So we've done this for desktop QML. So it's fully compatible. If you have a function in a QML file that you'd like to share for your microcontroller project and a desktop project, you can do the same thing there, and it'll work. And it'll even generate you invocable meta functions that has a nicer C++ syntax signature. So it doesn't create like doesn't take a Q variant or anything like that. So if you have a function like pick color that returns a color in upstream QML, it's a C++ function that returns you a Q color, the RGBA32. Properties are already typed, so we can figure out what those mean and what those are and what's used inside the expression. We can infer everything, and this was pretty ambitious, but it worked really, really well with the little annotations to the helper functions, and the rest we can figure out. And the result is everything's a lot more efficient. It can be interpreted and a lot more efficient than regular interpreted generic type of things, and this is a lot more specific. So this also allows us to detect type errors at compile time when they turn into compilers, which is generally a very convenient feature. So of course, with the MCU project, the main primary objective was to efficiency, and we've made great strides in that area. So this just about covers the building blocks that I wanted to talk about. One last thing, 1.1 is out. Things that we've talked about today are generally available in the release. Quite a few things we didn't talk about here are there as well. There's there's about 200 new pages of documentation that have been added to the docs with Quick Ultralight 1.1. We've been getting great feedback, and quite a few tweaks and updates are already in the pipeline. We continue to listen to your feedback to make it work. And there's optimizations being made constantly, and the Q Ultralight's only getting better. So a special thanks to Johan and Ari for inviting me to this talk, Simon for making the original, Johan, Ari, Jessica, Christian, Olivier, and all the R&D team for helping me understand the product. And if you guys would like to do a short survey, please go ahead. That's it. That's my talk.
Okay, thank you for the informative session, Devinder. If there's any questions, please use the Q&A pane in order to ask them, and Devinder will respond to them live.
Okay, so one question was, you're using Visual Studio as opposed to Cube Creator. Is there a reason for that? I actually use Cube Creator for most of it. Only to display the folder structure, I use Visual Studio Code. I'm just used to that, that editor. It's something that I use to write all my documentation and to check file structures. It was just easier for me to do that and switch between the two. How is the code gen from QUL to C++ done? So some of the underlying QUL might be C++ already, if that's what you mean. For the QML itself, there's a tool under the hood that basically converts the QML to C++ that we have in place. If I don't know if you need a more detailed answer to that, but please feel free to reach out over email, or my email's right there in that slide if you need more than that. It is possible to runtime to dynamically load from Flash. Okay, is it possible? It is possible at runtime to dynamically load from Flash precompiled ML views and show them. Sort of plugin where I can add new QMLs without adding them statically. No, all of the QMLs, I believe all of the QML files actually do need to be compiled into C++ and .h files. So I don't believe that you can do that. So to reiterate, the question was, is it possible to, at runtime, to dynamically load from Flash precompiled QML views and show them a sort of plugins where I can add new QML views without adding them statically to the main program? Yeah, if I understand the question correctly, I think, you know, can we do it without actually the compile step? Then no. If I'm misunderstanding it, then please feel free to email.
I think because those have to be static, they're statically linked. I don't think that we can dynamically load them even if they're precompiled. So.
Yeah. Exactly. I think that's the gist of it.
There were quite a few others that I think we covered as well during the course of the talk.
Oh, great. Yeah, I guess if we have a couple minutes, if there's something I didn't say right, or if something needs explaining, I can do that. Otherwise, we're more or less done. I do know towards the end I was kind of rushing, so that might not have been super clear.
I know there was a lot of interest in some of the new syntax in the C++ for property definitions and some of the optimizations to QML. And I know that a lot of that is coming into Qt 6 development effort.
Yep.
So that is something that we're excited to bring to the community at large with that release.
Yeah, and in fact, I want to reiterate that the document page for the Qt Ultralight has been completely redone. Most of my talk actually, well, a chunk of my talk comes from the document page. So if you have questions about how to do something in CMake, or if there's options for something, chances are you will find it there. 200 new pages were added, guys. So it's a lot of content. And again, you know, feel free to send me questions.
For sure. Another common question was about performance benchmarks. And you know, I shared some of the benchmarks we have for some of our demos. But the reason that's not publicly published at this point is just because it's so dependent on the board and the assets that are chosen to create your user interface, that it's really difficult to give a definitive, you know, minimum for a meaningful project or a maximum, right?
Right.
But again, we are happy to share the stats for our demonstrations with any customers who are interested in engaging with us on the Qt for MCUs offering.
Okay, I guess if that's done, Iris, do we just close this down, or do we just stick around for, what is it, another 5 minutes?
No, we can close this down. So let me just give the final remarks. So as we're getting to the end of the session, please note that, again, you can use that link to send us some feedback or join the next session via that page, www.qt.io/thank-you-survey.
Oh,
you can also access the Qt Professional Services team on live chat through that same page, which will take you over to the live event portal as well. So if you're looking to, you know, work on your MCU project now, they're also there to support you on a one-to-one basis as well. So this concludes our session here today. Thank you again, Devinder, for your support and contributions here, and everyone for attending.
Yeah, I almost forgot to say thank you to Iris and Corey. I'm so sorry, guys.
Oh, no, it's our pleasure.
There are a couple other questions that popped up here in the last minute.
We do have 3 minutes. So has the presentation been recorded and will it be available for download? I know it's been recorded and will be available for viewing. I don't know about download. Iris, you want to take that one?
Yeah, sure. So if we have the presentation from the presenter, we can add it to the session. So we'll add Devinder's over to the same tiles that are used for the live sessions on the live event portal and upload it there.
Okay, so that's done. What are you working on Qt Ultralight right now, and when will it be available? So Qt Ultralight just released 1.1. I think the goal is to release 1.2. I don't know what the timeline is off the top of my head, but it's pretty aggressive. I think it's in like 6 months or less.
1.2 should be out in actually about 1 month.
Oh, 1 month.
Yep.
Great. Okay. What are we working on it right now? I know there's more board support coming, but Corey, do you know more details about this?
Yeah, some of the big functionality that's coming in is support for the use of the design studio to bring Qt Ultralight enabled UIs directly over into an MCU project. So we're excited about that a lot. And yeah, additional board supports, additional debug support. I saw there was a question about debugging. It is possible to do debugging. With the 1.1 release, our primary method is supported through command line.
Yeah, GDB, yeah.
And that with the 1.0 release, we had kind of a backwards way of you could get actual visual debugging supported. And that's coming in more full support with 1.2 as well. So we're constantly working in that direction.
There's another question here about does the display color depth a bit matter for handling color blending of foreground images on dynamic backgrounds? How about transparency? Thanks. Honestly, Corey, do you know more about this? I'm not too familiar with this topic.
You know, I know generally about that tech, but I don't know specifically how much it matters. So obviously that's going to impact the size of the application, but I'm not sure about the compositing and blending.
Yeah, and
I know we do support transparency, but on our reference platforms, but I don't know about the depth bit.
Yeah, this might be a more in-depth conversation. It also depends, I guess, what your board supports. So if you want, you can reach out to me. Oh, this is actually Taichi. I know you. And yeah, you can reach out to me after and we can discuss it. I think we're all set then. Thank you, guys.
Great. Thank you very much again. And you can join us in our next session or feel free to contact us through that thank you survey page too. Thank you.
Thank you.